We'll begin a brief overview of the Lorenz attractor. We'll start in this video by giving some background information. When we first looked at fixed points, it was in one dimension on a line. If initial conditions didn't start directly on the fixed point, one of two things could happen. A trajectory could approach the fixed point, or a trajectory could go to infinity. When we moved to 2 dimensions, the plane, the number of things that could happen increased. A trajectory could still converge to a fixed point or go to infinity, but it could also move in closed orbits. So this raised a natural question. If we move to 3-dimensional space, can we see an even wider range of behaviors? The man who answered this was Edward Lorenz in the 1950s. Lorenz wasn't coming at this from a mathematical curiosity. He was a meteorologist, and he was struggling with a very concrete problem. You see, in 2 dimensions, it doesn't really matter where precisely a trajectory starts. Suppose you have a trajectory that starts at -8, 8. It does whatever it does. Maybe it gets caught up in an asymptotically stable orbit like so. But you know that in the real world, there are always measuring errors and rounding errors and random factors. Maybe you think you're starting at -8, 8. But due to these random fluctuations not included in your model, you're actually starting at -8, 8.00000001. Well, it doesn't really matter. The trajectories do basically the same thing. Of course, if you started way over here, that would change things. But minor errors in your starting position, like this, won't cause major errors down the road. Well, this was very much not what Lorenz was finding when he tried to use mathematical models to study the weather. These models weren't in the plane, they were in higher dimensional space. And what he found was that minor errors up front could lead to completely different behaviors down the line. A 0.0000001 error in your starting condition could cause you to go down a completely different path. Lorenz famously described the situation in the following terms. Suppose a point in space represents weather conditions. We are drawing this on a plane because we can't draw in higher dimensions, but actually every point stores humidity and temperature and wind speed and hundreds of other conditions. Well, suppose that this set of weather conditions represents a tornado, and this set of weather conditions represents a harmless rain shower. We can use the current weather conditions to predict the future weather. Say we look at the current conditions and we follow the trajectory and we predict that there's going to be a tornado. What Lorenz claimed, maybe a little hyperbolically, was that the model is so delicate that if a butterfly flaps its wings and infinitesimally changes your initial state, a tornado might no longer occur. This is categorically different behavior from up here, where minor changes in your initial state don't matter. So clearly something was happening in Lorenz's weather models that couldn't happen on the plane. Trajectories weren't going to fixed points or following nice trajectories to infinity or moving in nice circular paths. They were doing something that allowed minor perturbations in initial conditions to completely change the system, the state of the system. And Lorenz wanted to figure out what that something was.